Yo, what's up? It's your boy, Mr. AC. And what I got for you guys today is going over primarily, and we are on year number. So let's go ahead and get started. All right, let's go ahead and get started with our very first video on second FTC, the second fundamental theorem of calculus. Now, this 1999 problem is a pretty good one to just go over. So, you know what I'm saying? Let's go ahead and go over it. I think it's a good one, and I think it's a great one to actually start with. And again, the cool thing is you'll notice the progressions as we go through. You're just gonna see how problems slowly get harder and harder. So let's just get started. The graph of f consists of 3 line segments is given above. So here's the good news. They told us that they're giving us f. So this graph is f. And then they said let g of x equal the antiderivative of f, essentially. Now, that's good to know. So for example, if I want to complete it says compute g of 4 and g of negative 2. What that's telling us is in order for us to even solve these out, we need to plug them into our function that's right here. So really we just need to plug these in, and then we're going to see what we get. So for example, let's plug them in just like you normally would. We're going to get g of 4. So we get g of 4 is equal to the antiderivative of 1 to the 4, not to the 4th, but basically 1 to 4, 4 to 1, f of t dt. Well, what is that? What do we need to do? Well, what does the antiderivative tell us to do? Well, the antiderivative tells us that we got to take the area under the curve from 1 to 4. So I'm going to go to this graph and I'm going to draw basically what I see is a trapezoid right here. We got ourselves a trapezoid there. And then the good news is if I look here from 2 to 4, we get triangles, a triangle here. And we get a triangle here. Now, the good news is we don't even need to compute these because we know they're going to cancel each other out. This is positive and this is negative, and they're the same. So all we need to do is compute this trapezoid. Well, what's the area of a trapezoid? It's L1 plus L2. That's your 2 lengths divided by 2 times the width. Let me put the width better right there. So what's the length 1? Well, L1 is 4, so 4 plus, what is L2? L2 is 1, so 4 plus 1 divided by 2 times our width, which is 1. So we get 4 plus 1 is 5, 5 divided by 2 is 2.5 times 1, we get 2.5. So this is going to equal 2.5. That's going to be the area under the curve from 1 to 4. Again, I could care less about the 2 to 4 because we're going to get an area of 0. All right, let's move ahead and go back to our next problem, g of negative 2. So we're going to get g of negative 2 equals, let me go ahead and write it out. So the next one says to compute g of negative 2. Now, the thing about this is when we do this, remember our integrals, they need to go from most positive, right? To most negative. So most positive, I guess I should put a plus sign, not a number sign, to most negative. This goes from negative 2 to 1, so we got to flip these, right? The 1 should go up here, and the negative 2 should go down here. Now, in order for that to happen, I don't know if you remember this, that essentially means, it's essentially like if you're finding the area under the curve, you're flipping the sign. So if you flip the integral, that means you're flipping the symbol, which means if the area was positive, it's actually really negative. If the area is negative, it's actually really positive. Now that may seem confusing, but all we really do is just put a negative 1 in the front right here. That just represents the flip. So now we've got the flip perfect. Now we can find the area under the curve. And really, I like to just do negative 1 times whatever my area is going to be here. So let's go from negative 2 to 1. Negative 2 to 1 is a triangle. So let's do the area of a triangle. Length times width divided by 2. We get 1, 2, 3. So 3 times 4, because this height is 1, 2, 3, 4, divided by 2. 12 divided by 2 is 6. So we get length times width divided by 2. We did that right here. We get 6. So we get negative 1 times 6. Which is going to be negative 6. So there it is. This is going to be my 2 answers for part A of this problem. Hopefully that made sense. Let's go ahead and move on to part B. All right, moving on to part B. It says find the instantaneous rate of change of g with respect to x when x equals 1. Well, what does that mean? Well, instantaneous rate of change means the derivative, right? Instant. That's our derivative. We're not doing average, we're doing instant. So we got to take the derivative of g because it's asking about g. So we already have this expression here. So why not take the derivative? So we take the derivative, shazam, like this. Now this is the second fundamental theorem of calculus. This is that second rule that we've learned. We're going to take the derivative with the antiderivative. That's basically going to cancel each other out, right? You're taking the derivative and then you're doing the antiderivative, then you're doing the derivative. So really, if you remember, what we're going to get is derivative anti cancels out and we're left with our function here, right? Because we're just going antiderivative, going derivative, we're going back to where we started from. This is going to be f of x, right? Because when I take the antiderivative, I'm going to plug this in right here, and then when I take the derivative, I'm basically going to get right back to where I started. So we plug this back in here times, don't forget the second fundamental theorem of calculus always says that we have to take the derivative of this upper bound. We don't have to worry about this bottom bound because the bottom bound is 1. When we plug into 1, it's just a number, but this is a variable. Well, what's the derivative of x? The derivative of x is 1, so times 1. Again, in this case, because it's a 1, we don't have to worry about it, so it's just f of x. So now we have this expression, g prime of x is equal to f of x. So now we can finally plug in 1. So we're going to get g of 1, g prime of 1 is equal to f of 1. Now, how do we get that? Well, what is f? Well, luckily for us, they gave us f. F is right here, right in this graph. So what is f of 1? Well, f of 1 is 4. That's just actually the y value, right? It's right up here. So g prime of 1 is f. Well, we got to look at f. F is the graph. Well, what's f of 1? F of 1 is 4. So then we have figured out the instantaneous rate of change of g. Pretty nice, pretty tough one, but hopefully that made sense using the second fundamental theorem of calculus. That's why it's called second FTC, because we're going to deal with this quite a bit. All right, let's go ahead and move on to part C. Find the absolute minimum value of g. Now, if you remember, absolute minimum value means the smallest y value, right? We are talking about y values of our function. Now, we need to find what is the smallest y value of this graph. Well, we always check our endpoints. So hopefully this is somewhat coming back to you. This is obviously just g. We're going to plug in -2. I'm going to leave space in a moment because I don't know if you remember this. I'm going to go ahead and draw it out in a moment. We need to find these values. The good news is this. According to part A, we already did g of 2 and g of 4, right? These are the y values. G of -2 was -6 and g of 4 was 2.5. So from part A, we can already go ahead and write -6, and then this was 2.5, okay? Now, why do I leave this blank? Well, if I was to draw a graph, we need to check the endpoints right here and right here, but we also don't know how far the relative mins and maxes dip. For example, right here, we don't know how high this is, and we don't know how low this is, right? This might go all the way down like this, so this might be the absolute minimum. So we need to take the derivative of our function, so we need to do g prime of x, which we already got, and we need to figure out when exactly does it equal 0, because we want to find when does it have these, where are these bumps located at? And then after we do that, we need to do some analysis, right? What's the value of the relative min or max? So let's go to our graph and let's find out, okay, when is my derivative slope 0? Well, this is the graph of f, right? So I need to take the derivative of this graph so that it can be g prime. Well, I just need to look at f. My apologies. I need to look at f. This is giving you g prime, which is just f. We are given f, and we need to find when it's first 0. I can already tell that it's going to be 0 right here, right? This is 0 because g prime is just f. There is no other spot here except for the endpoints that it's 0, which we already have that value. Well, what is 3? Well, 3 changes from positive to negative. Positive to negative. Positive to negative is a relative maximum. Now, that's good to know because this problem is asking us for an absolute minimum. We actually do not have a minimum on this graph because it doesn't change from negative to positive. So that tells us from this interval, well, guess what? It looks like this is our absolute. So how do I justify this? Because we don't have an absolute minimum. We only have the endpoints. We're going to go ahead and write down. I'm going to change the font. Let me just write it out real quick and see if it'll make sense. Okay, So this is what I wrote down for my justification, and let's see if this makes sense. G does not have a relative minimum because G prime of x equals f of x does not change from negative to positive. So we are concluding that we tried to find a relative minimum, but we don't have one. Therefore, the absolute minimum is -6 because it's one of the two endpoints, right? So this is hopefully getting clear that we tried to find a relative min to see if there was a bump that went down so that we can compare it to this endpoint here, but nonetheless, there wasn't. So because of that reason, we can conclude that the absolute minimum is -6, right? Absolute minimum is y value. The y value is -6. Hopefully that makes sense. That's a pretty tough one. Okay, let's go ahead and go on to part D. The second derivative of G is not defined at 1 and 2. How many of these are points of inflection on the graph of G? I'm going to move the graph slightly just so that I can, read the question just a little bit carefully. How many of these values are x coordinates of points of inflection? Okay, cool. Let's go on to part D. To be a point of inflection, okay, what that means is to be a point of inflection, that means our second derivative G double prime of x equals f prime of x, okay? Number one, it has to change signs. So we need our second derivative to change signs. So if we go, this is the graph of f right here. So we need to take the derivative of it because we're talking about the graph of G, which is G double prime, and that is our point of inflection. Well, G double prime at 1, okay, obviously it's undefined, but that's not a big deal because remember, we need just the second derivative to change signs. Well, look over here. This goes from positive to negative. Positive to negative because we're taking the derivative of f. This is the graph of f. We're taking the derivative. So the graph right here is positive slope and the graph down here is negative slope. At 2, it's not defined because we get a cusp. But what does that change from? Well, that changes from negative to negative. So you can see which one of these is a point of inflection. Well, it's only this point right here. And how would we write that out? Well, this is how we would write it out. So this is our justification. We'll say the graph of G has a point of inflection at x equals 1 because G double prime equals f prime of x changes from positive to negative. At x equals 2, G double prime of x equals f prime of x does not change signs. Therefore, it is not a point of inflection. That should say, by the way, that's my apologies. That should say does not change signs. I don't know what I said with does not have sign changes, does not have changes. My apologies, there it is. Does not change signs, therefore it is not a point of inflection, okay? And that's what it means to be a point of inflection. So hopefully that's making sense. Well, there it is, y'all. Hopefully y'all enjoyed a pretty tough one, but I felt like this was a really fair one and kind of leads us into our next ones because it talked a little bit about antiderivative, a little derivative, a little absolute min, and our second derivative point of inflection. So hopefully y'all enjoyed. I'm out. Take care. Capiche?